So the last section will tie in with your second section and hopefully help you understand the second section better. So there's 3 rules to determine electron arrangement. So today we are totally studying electrons' position, where they're at. Remember, I can study an electron's position, I can study an electron's speed, but I can't do both at the same time. So today we're all about position. Where are the electrons at? So we will talk about Pauli's exclusion principle, Aufbau principle, and Hund's rule. So this is something that electrons follow. And then we'll learn how to draw an electron dot structure that shows how many outside or how many valence electrons something has. So a valence electron will be important. You'll need to know what that is. These 3 rules or principles, make sure that you know the difference. What does each one stand for? So that's kind of the introduction. So here's your first set of notes. The arrangement that the electrons have in an atom is called the electron configuration. So we are going to look and find where each and every electron goes in your different atoms. The Aufbau principle states that electrons occupy the lowest energy orbital available. Electrons are lazy. They want to be in ground state, and they always want to be in the lowest energy level possible. So if I look at a lot of our energy levels, so here's energy level 1, energy level 2, energy level 3. First electrons are always going to go in the bottom. 2 will go here. 2 will go here. Then 2, then 2, then 2. And they'll spread out. I should say 1, 1, 1, and then refill so that 2 can go here. But I am going to always start at the bottom level because electrons want to go to the lowest level first. So Aufbau principle, electrons start at the bottom. They're lazy. Aufbau is the lazy principle, basically. Features using that diagram. All orbitals related to an energy sublevel have equal energy. So wherever those boxes on the prior diagram are your orbitals. So if I have 3 orbitals lined up, like you did in your 2p, all of those have equal energy. All 3 of them are the same. In an atom that has many electrons, the energy sublevels have different energies. So my 2s, looking at your diagram again that you have, my 2s is a little bit lower than my 2p. That means that the 3 2p orbitals have more energy than the 2s. The higher up you go on that diagram, the more energy there is. If I look at increasing energy, the sequence is S, P, D, and F, and we'll talk about that. So if you look at your energy level 1 at the bottom, there is only an S, because 1 can only have 1 sublevel. If you look at 2, there's a 2s and a 2p. If you look at 3, there's a 3s, 3p, 3d. If you look at 4, there's 4s, 4p, 4d, 4f. And then I can go up from there. Orbitals related to the sublevels can overlap other sublevels. Basically, that means, looking at your diagram again, if I look at my 4s, it has less energy than my 3d. So just because my number is bigger does not necessarily mean that it has more energy. That's what the last one says. Okay, Aufbau. Electrons are lazy. They stay at the bottom. Pauli exclusion principle states that a maximum of 2 electrons can occupy a single orbital. So any orbital, I don't care if it's a 4s orbital, a 5d orbital. Any orbital can only hold 2 electrons. So those little boxes on your diagram can only hold 2 electrons. It might hold 1, but at maximum it can hold 2. So Pauli exclusion principle, a maximum of 2 can occupy a single orbital, but they have to have opposite spins. So they are not going to spin in the same direction. And the way that we show our spin is with these arrows. So notice one is up, one is down, up, down. They are never going to have the same spin. You'll never have 2 arrows pointing up. And then Hund's rule states that the single electrons with the same spin occupy each orbital before they fill another one. So if I have any of your P's have 3 boxes. So 1 electron will go here, 1 will go here, 1 will go here before it comes back and fills another one. So Hund's rule I kind of call the bedroom rule. Most people prefer to have their own room as opposed to pairing up with somebody. So Hund's rule states that I'm going to occupy my own space before any other one is going to come in and fill it up and put 2 in there. So it's going to spread out first. And the lab that we do will also help very much with that. Table, I would like you guys to do this table. You're going to plug things in. I'm not going to show that up here right now. And the lab, that lab we might get to and might not. So the Aufbau diagram can be used to write ground state electron configurations for all elements up to atomic number 23. When we get to certain transition metals, and I don't expect you to memorize any of them, but I expect you to know that this happens. For certain transition metals like chromium and copper, half full level is more stable than like 3/4 or 7/8 or something like that. So some transition metals don't follow all the rules. And chromium and copper are examples, and when we do the lab, I'll show how one of those work. So up until 23, so for the main top part of the periodic table that we use, the most common ones, you're going to use those rules. It'll work for everything. When we get to transition metals in the middle of the periodic table, sometimes they do things a little bit differently. Okay, valence electrons are the outermost electrons. So taking the periodic table that I have made a copy of for you, look at calcium, since that's the last one that we've kind of worked with. Calcium, what is the atomic number for calcium?
20.
20. Its symbol is?
Ca.
So look at the electron, the abbreviated configuration at the side of the box. Calcium is what?
2882.
2882. This is how many valence electrons calcium has. If I look at sodium, it's going to have 1 in the outside. So it's going to have 1 electron. If I look at neon, what is neon? 2, 8. It has 8 valence electrons. So your valence electrons are your outermost electrons, and they're associated with the highest energy level. So here'd be my first energy level, here'd be my second energy level. These have more energy than these in here. I can show my valence electrons by using an electron dot structure, or I call it an electron dot diagram. You write the symbol, so Li for lithium, has 1 valence electron, 1 dot. Beryllium has 2, boron has 3, carbon. And this table is in your book. So for homework purposes, I expect you to put the dots in order where they go. Test purposes, if you know that nitrogen has 5 valence electrons, and instead of putting the 2 dots at the top, you put 2 at the bottom and spread them out, I won't count that wrong. But as long as you have the table, make sure that you use that to see where your valence electrons are. So, if I'm going to do an electron dot diagram, I am going to find tin. So it's asking me to look up tin. So find tin on your periodic table. 50. Okay, 50. What is its symbol? SN. So I'm going to write down the symbol for tin. If you look up in the right-hand corner, what's the abbreviated configuration for tin?
2, 8, 18, 18, 4.
Okay. So how many valence electrons does it have? 4. 4 is the outermost. So tin will have 1, 2, 3, 4 dots. Because it has 4 valence electrons. And that's how I would draw them. And then here's just the review of everything again. I want to point out something that you need to know that's not in your notes. So look at page 160. It's going to have a diagram for you. And I write my diagram sideways. So to be totally honest,